Year 12. Quickly, we're going to talk about purity. Small little concept that we can tack on with yield. All right, let's just get into it. Excuse me. So, because some of these processes, some of these synthesis processes don't produce only one product, you have to do some refining and separation techniques to get your desired product. And you can't completely remove everything else. So we talk about the purity of some thing that we were trying to make. Okay? You can also buy reagents in different purities. Okay? And you need different purities for different types of experiments and different types of things. Words. Okay, there's several levels of purity that we commonly talk about in industry. Increased purity requires more exacting conditions and more refining steps. So the higher the purity, the higher the cost in what you're buying. So you have stuff like technical grade is used for non-critical lab work, including rinsing and dissolving. They're usually cheap reagents, so technical grade reagents. After that, you get going up in purity, synthesis reagent grade, so suitable for organic synthesis, making stuff. After that, you've got analytical grade. It's suitable for when you're doing analysis to kind of what's the word that I'm looking for? Small concentrations and stuff like that. So good in research and quality control purposes, very expensive. And the top one, pharmacological grade, these need to meet the needs for human consumption. So we don't want any trace elements in there. We want it as high purity as possible when we're putting it in our bodies. Okay, so that's just a bit of theoretical overview on purity. We're going to use this formula to calculate purity. So it's essentially not that difficult. It's just the mass of what we're after over the mass in the sample times 100%. Okay. So just a little bit more on the theory. I chose to use some examples here that I pulled off of different websites. Here's some white sugar from, it looks like Woolworths. $2.60 for, I was going to say 100 grams for, what? Oh, look, it's right there. It's 3 kilos. or it's 9 cents per 100 gram. And so that's good enough for eating and food and stuff like that with sugar. Pharmaceutical, secondary standard. Okay, so pharmaceutical grade, we've got 1 gram of sucrose for $106 there, Australian. And here I think is some other sources. What have we got here? Different sizes, I'm not too sure. Oh, here we go. It's greater than 99.5% sucrose. Okay, so you can buy 10 milligrams for $30. You can buy the 5 kilos for $264. So you can see that the higher the purity is, the more expensive it is. It's harder to get it that pure. I was just talking about pharmaceutical stuff about putting in your body, wasn't I? And then, of course, we eat white sugar all the time. More like intravenously injecting it and stuff like that. Anyway, so there's enough theory on purity as long as you got the idea of there's different grades of purity for different roles in chemistry. Very broad brush there too. And that the higher the purity, the higher the cost, of course. Okay, and you've got to go to the right source. You can't go down to Woolies asking for greater than 99.5%. There's a skit in there. Okay, example. Chalk is a form of calcium carbonate. A paleontologist determined the calcium carbonate content of a chalk layer by reacting it with hydrochloric acid and capturing the carbon dioxide produced. So it was found that a certain size sample produced a certain volume of carbon dioxide gas with excess hydrochloric acid, determined the purity. Okay, so we're using a reaction here. So calcium, green's not good on blue, is it? Dark blue. Calcium carbonate, solid, and we're reacting it with hydrochloric acid. and it's going to, calcium chloride, and that is soluble, plus water, plus carbon dioxide. Okay, I'm balanced, aren't I? That's why I put the 2 there. Yep, okay. So from the question, well, we had a 2.6 gram sample, but we don't know if we had 2.6 grams of calcium carbonate. But what we do know is 540.9 milliliters of carbon dioxide were produced. From there, we can go back, so we can find the moles of carbon dioxide, we can go back and find the moles of calcium carbonate, and then the mass of calcium carbonate, and then use the formula for percentage purity. Okay, so 504.9, so we've got moles of CO2 is going to equal 0.5409 litres multiplied by, oh no, it's divided by our molar volume of gas. So our molar volume of gas, is it 20? Teach me to have it right in front of me, won't it? Oh, here it is. Sorry, guys. 24.79 litres per mole. Divided by 24.79 litres per mole. And so I work out how many moles of carbon dioxide were produced. 0.5409 divided by 24.79 equals 0.0218 ... I'll keep it in my calculator, mole of CO2. So then our moles of calcium carbonate equals the 0.0218 mole of CO2 times by the fraction of CO2 to calcium carbonate. What's in front of each? 1 to 1. So it equals 0.0218 mole of calcium carbonate. So the mass of calcium carbonate equals 0.0218. What's in my calculator? Moles times by the molar mass. I forget what calcium is off the top of my head. 40.08 plus the 12.01 for carbon. Oh, plus the 3 times 16 grams per mole. It's becoming a bit messy. That's my trademark. Times the by brackets 40.08 plus 12.01 plus 3 times 16. So I get 2.1883891 grams. And that's really promising because it's less than my 2.6 gram sample. If you're getting a number that's larger than your sample size, alarm bells should be ringing, you've done something wrong. So my percentage purity equals how much was actually calcium carbonate, which was the 2.183891 grams, divided by my sample size, which was 2.6 grams, multiplied by 100. I forgot that. Divided by 2.6. 83.99. 2 sig figs, so that's 84% purity. Alright. There's a little worksheet for you to do. Hopefully that helped you out. I'll talk to you next time.